Okay, so today we're just gonna look over the solution of midterm 1. I'll demonstrate how to do the get the answers and kind of why we do each steps. So let's look at the first question. So the first question is asking us to design an op-amp voltage amplifier circuit with the appropriate load resistors that our final result should achieve something like this graph, where VI is, in this case, we can just say that VI is around, V out is equal to 10 times of VI. So it's being amplified 10 times. However, it's also being clamped at any values that are below and below. So V out is also maxed at 8 voltages and mid at -8. So it's in between the range of positive and -8 voltages. We are also given that the values of our ideal op-amps. When we look at this, we can quickly see that our resaturation value is not going to be super useful here because in this case, our op-amp only gets saturated when the voltage is above and below 17 positive and negative 13 voltages, which in this case is too big or too small, so it doesn't really help us. So what we will have to do then is we will have to look at the current, and we will need a load resistor to work with the current so that we can using the maximum output current this way to limit the maximum voltage or the minimum voltage. So basically for this question, when we design our circuits, there's two things we have to consider. Number one, we will need two resistors to create this op-amp to make that the input voltage 10 times. So output voltage is 10 times the input voltage. And we also need a load resistor so that limit using IL max, it's going to limit the voltage at max A voltages and minimum -8 voltages. So now let's start working. Let's first start drawing a diode. Sorry, so not a diode, an op-amp. So negative terminal, positive terminal. Let's put this as our input voltage, and let's put it over here as our output voltage. Now, let's put a ground here so we can get a resistor value out. And we want to make it a negative feedback loop so that we can actually achieve our result. If there was no feedback or if it was a positive feedback, it would just always be saturated. It wouldn't really give us this actual, this actual sine wave amplifying circuit. So we need to connect the negative terminal with the outputs. And we will also want another resistor over here as VR so that it's going to work with the output current to limit it. Now, why do we, I forgot. So there should be two voltage resistors, one over here. So why do we have two resistors? Well, we're trying to mimic something like, for example, what we would do for a voltage divider, but this time is amplifying it. We're using two resistors so that we can actually create this relations where VI is going to be proportional to V out at a certain value. And in this case, we want that to be 10. So let's do the first part. Okay, before that, let's draw some things we know already. So I negative, I positive. So since we know this is a ideal of op-amp, we know that there will be no current flowing into the op-amp. So VI and V negative, or I negative and I positive are both going to be 0. Another thing we will know is that this is going to be very useful for us to know that nothing's flowing in, is that if we, let's say, draw another current here, let's call this I, it's just going to flow over here since there's no current flowing into the diode. Now let's do another current. Let's call this IL, and let's mark the current going out. So now let's also, for simplicity, mark all the resistor directions so that it's more clear to see. Okay. Another thing we would know about, since it's a negative feedback, we know that V positive equals to V negative. So the voltage at the positive terminal is equal to the negative. Now, coincidentally, our input voltage equals to V plus. So V plus equals to V negative and also equals to VI. So in this case, we can actually trace a node voltage over here. This voltage, the voltage at this node is just going to be VI because the voltage of this node is V negative, which means it's just, and that's equal to V positive, which is then equal to VI. So this is some things we already know about the circuit. Now let's actually start working on it. The first thing we want to do is we want to create that amp. We want to make so that V out is 10 times VI. So to do that, we will have to find a value of R1 and R2 that satisfy this equation. So let's do that. So we know that VI, if you do a KCL, since this is ground, VI is just going to be equal to the voltage of this. Oh, sorry. The voltage of the sneeze coming didn't come. The voltage of the resistor voltage over here. So it's equal to 0, the ground, plus I, the current flowing over here, times R1. So the resistor voltage, which is just equal to R1 times I. Now, the second thing we will look at is V out. So if we look at here, V out is very similar to VI. So the only difference is that there's another resistor voltage over here with R2. So it is still kind of so V out in this case is just equal to I times R1 plus I times R2. So two of these. If we were to simplify that, we get this. So now this is very good because we have found a way to express VI and V out both with our variable I. So they have so now if we sub in those two or cross out those two, we can get a equation that isolates, just only has VI and V out, so that we can find, the proportion of those two and then assign VR1 and R2 to be the values that gives us the proportion we want. And in this case, we know that because the proportion we want is 10. So we know that our VO divided by VI is equal to 10. That is the goal of our design. So if we were to plug those numbers in to get, so if we were to plug in the equation over here with the equation over here, we get R1 plus R2 times I divided by R1 times I. So VI goes here, VI goes here. So now we have, and then we can cross this out. So right now, there will be more than one, there are definitely more than one resistor values, like there's infinite many pretty much, that will achieve this thing. But in our case, we just need any resistor values for R1 and R2 that will satisfy this equation. We can also simplify this so that makes the next step easier. One, so R2, R1 equals to 9. So we just need R1 to be 10, R2 to be 9 times R1. So in order if this satisfies any resistor value satisfies this, will create this 10 times, VI equals to 10 times VI. So in our case, let's just say R2 equals to let's say let's pick a number. Let's say 18 kilo ohms, and R1 equals to 2 kilo ohms. So in this case, if we put it here, it equals to 9, it satisfies the equation. And if you were to design R1, R2 with these values, it would create this. It will times the input voltage by 10. But now we want to do the second part. Now we need to find RL. We need to find a value of RL that will give us this clamp at positive and negative 8. We have to, so let's write down. So we know that IL max with the diode that was given to us is that it will max at 20 milliamps. And our goal is to do using this value to create a V out max at 8 voltage. So now we have to adjust our, and I guess same thing if we are min at negative 20 milliamps, and then that will create the negative 8 for V out max. But since they're both the same thing and voltage is resistance is a constant, it would just fault the sign, so that we wouldn't really have to consider negative case. So our goal right now is we can just find the positive maximum case. So now let's look. So now we want to find an equation where we can express RL, I out, V out max, so V out and V in. Sorry, I forgot V in max. So we want a way that we can express all these in a equation so that we can adjust RL to be the value that would minimize it according to our values. So let's write down the equation that will relate these two. So if you do a KC over here, we know that I out equals to I out plus I. So in this case, we just have to find it relates to I and relates to IL. Let's do IL first. IL is very simple. So since we know V out is over here, IL with just a standard Ohm's law, we know that it's equal to V out divided by RL. So that's our first part. Now we want to find one that expresses with. If we look over here with VI and V out, we can see another KC out is that VI, V out is actually equal to VI plus the resistor voltage of R2. So plus R2, because since we already know R2 from our previous design, let's sub in R2. And let's now isolate I. So 15 kilo ohms times I equals to V out minus VI, and I equals to V out. That's 18 kilo ohms. Now that's fantastic. Now we have the two equations for VI. Now we sub this back into I out. We will have an equation where we can express I out with VI, VO, V out, and RL. So let's do that. Okay, that's great. So now our next step is to plug in these values because we were trying to create a condition. So when IL max goes to this, when VO max is this, when IL goes to this, RL equals to whatever. So if we plug in these, so 20 milliamps, so IL max, at max is 20 milliamps, 8 voltages, RL plus 8 voltage minus 1 voltage plus 10 kilo ohms. 8 kilo. Okay, let's do 7. Let's do a calculator. 7 divided by 18. That gives us 0.7. 3889 milliamps. So 20 subtract that would give us 19.611. And oh, oops, that should go to a different line. Milliamps goes to 8 volt, RC. And then we can get the value of RL equals to 8 volts, which is divided by this, which equals to, let's do some more calculator, 0.468, roughly equals, let's do that. So if we were to set up RL to be 4.8 kilo ohms, 0.48 kilo ohms, it will cut the circuit at positive and -8. So now let's rewrite everything so that we have our answer. So let's circle this. And we know that R1 equals to 2 kilo ohms, R2 equals to 18 kilo ohms, and RL equals to, let me check, 408 ohms. So with this design, it will create this graph if we were to set up VI to be equal to this value, this function. So that's question 1 done. So once again, for question 1, our thinking was to first find R1 and R2, so we can create this actual, amplifier. We can amplify the circuit 10 times, and then finding RL that limits it at a value according to limited at positive and negative 8 voltages, and then since we use we out in accordance with IL. Sorry, I out, not IL. Okay, so that's question 1. So now let's look at question 2. So question 2, we are now analyzing a circuit involving a Zener diode. We are given these heuristics of the diode. So VDO equals 0.7 voltage, VZ equals to 3 voltages. We're told to analyze the circuit when it's off and when it's on. And we are told, for example, when it's off, what the value of V out in terms of VI and the range of VI that it would be on. And we're also told to do that same thing for on. So I redrew the circuit right here so we can better visualize it. So let's start by plotting let's define some variables. We're going to define ID as the current that's going to flow through the Zener diode. So let's do that. And we know that it's not going to flow this way, so it's going to flow this way again. Okay. So let's write down some things we know already. So we know that VDO equals to 0.7 volts, VZ equals to 3 voltage. And let's write down, before we start going into assuming diodes off and on, let's just first start by doing some KVL so we can find the relationship between these elements. So if we do, let's first find an equation we can express V out in relates to VI. And we can see that there's only one resistor voltage in between. So we know that V out is actually just equal to VI plus this voltage resistor, voltage resistor, which is going to be 1 kilo ohms times VD. So that's our equation for V out. Let's do the same thing for VI. So VI, let's find an equation where we can express VI with the voltage of the diode. So we know this is ground. So, and this is VI over here. So if we do a KVL over here, we know that VI is just going to be equal to all of these elements either added or subtracted. So in this case, VI is going to equal to first this voltage source subtracted by the voltage of this resistor . subtracted by the voltage of the diode, subtracted by another resistor voltage. Okay, and then let's simplify a little bit. And just like that, we have two equations that we will use. So this is our analysis of the circuit before we even start doing it. Now let's start doing some assumptions. Let's first assume that the diode is off. So when the diode is off, question one, we assume the diode is off. So let's first assume the diode is off. So when the diode is off, the first thing we know is that there will be no current flowing through. So VD ID will equal to 0. And the second thing we know for a Zener diode to be off is that it must be in between negative VZ. So the voltage of the diode must be in between negative VZ and VDO. It will be greater than VD if it's greater or equal. If it's greater than or equal to VDO, it's going to be on, and if it's equal to VZ, it's going to be Zener. So this is the condition for a Zener diode to be off. And let's stub in some values in. We get this. So this is the current when it's off, and this is the condition when it's off. We're gonna look at conditions later. Right now, let's first solve the value of VI out in relates to VI when the current it's off. So we made this equation later on, let's copy it over here. This equation expresses VI out with VI. So if we see right here, if we since we're already given the value of VT ID, we can just sub in ID and then get this and just get that V out is actually just going to be equal to VI. Since there's no current flowing through that resistor voltage, is just going to be 0. So now we have the first part of our first question. We have found the value of V out in relates to VI when the diode is off. Now moving on, we want to find the condition. Then let's copy our second equation that expresses VI with VDO. So let's sub in read ID. And then this will be gone, crossed out. And then let's isolate VD. I kind of crossed out the negative sign too. I don't like that. Okay, so let's isolate VD. VD equals to 3V so VI. And now we've created an equation where we express VD with VI. Now this is very good because remember the condition that we know before was a condition for VD, but that's not what we want. We want a condition that relates it to VI, the range of VI when it's off. And since we know VD is in between -3 volts and positive 2.7 volts, we know that this equation, 3 volts minus VI, will also be in this range since it's equal to VD. So let's do that. 3.37 volts. Let's subtract 3 volts on each side. And then now let's multiply each side by +1. So now if we see here, we have an equation of VI, the range of VI when the diode will be off. In this case, if it's in between if it's greater than positive 2.7 volts, 2.3 volts, but smaller than 6 volts, the diode will be off and V out will be equal to VI. So that's the first part of our problem. Now we want to do our second assumption and assume that the diode is on. Press too much button. Cut this in half. Now we want to assume the diode is on. Now, when the diode's on, we know that VD, the voltage of the diode, will just be equals to VDO. In this case, equal to 0.7 volts. Another thing we know is that for the diode to be on, there must be current flowing into the diode. So current VID must be greater or equal to 0. So now, with these conditions, we can start looking at our problem again. Let's first, once again, let's try to find a function of VO in relates to VI. So what we can do, we can't use one, we have to use both equations this time, so that we sub in one to the other. Since right now ID is equal to something, we can't just cross it out. We have to first express ID but now this time we know VD, we have to express ID in an equation with VI, so that we can sub in to the first equation to get an equation that only has VI and VD. That's our VI and VO. So let's first sub in VD for this one. And simplifying. Okay. And now let's isolate ID so we can express it with VI so we can use for later, sub in. And there we go. So now we have our first equation. Now what we want to do is we want to sub this in to our other equation so that we can now remove ID entirely and that only and have our equation where we can express V out with VI. So let's do that. So if we were to sub this in, let's give ourselves more space to work with. Okay, minus 2.3, this gets crossed out. Sorry, this gets crossed out. So it's actually just 2 divided by this. So VI minus 1/2 VI plus 1.15 voltages. V out is equal to 1/2 VI plus 1.15 voltages. And just like that, we have our equation for V out. Now we want to find the range where this happens. So now we want to look at this thing. And just with our luck, we already have our equation where we have isolated ID and then related to VI. So in this case, we want to express it. We want to express equation with VI. All we have to do is, sub this in with that. So since we know ID in this case has to be greater than or equal to 0, this must also be greater than or equal to 0. So let's copy this. This is greater or equal to 0. And then we can cross out the bottom. So 2.3 volts plus VI must be greater than 0. VI must be greater than or equal to 2.3 volts. Negative 2.3 volts, and VI must be smaller or equal to 2.3 volts. And just like that, we have our condition of when the diode will be on. And if you check it with our previous one, it makes sense because the two doesn't overlap. So when the input voltage is smaller or equal to 2.3 voltages, V out is equal to 1/2 of VI plus 1.15. And then when we keep on increasing VI to be greater than 2.3, but still smaller than 6 volts, the diode turns off, and then V out just equals to VI. And then if we keep increasing VI, it will reach the Zener point. But for this question, we don't have to worry about Zener region. Just we don't have to solve Zener region. So if we were to just write down, so let's just write down what we found. So diode off and diode on. So diode is off when it's in between 2.3 voltage and 6 volts, and it's on when it's smaller than 2.3 voltage. And in both our cases, when it's off, V out equals to VI. And when it's on, V out equals to 1/2 of VI plus 1.15. So this is what we found today. Yeah, so that's how you would do for question 2. Brief recaps. What we did was we first analyzed the circuit, and then we did 2 assumptions. We first did it when it's off, and then we expressed V out and VI when the diode is off, and then we found the range of VI when the diode is off. And then we assumed that when it's on, we found the value of V out and relates to VI when it's on, and then the range of when the diode is on. And then later on, we come up with this general solution of if VI is smaller than this value, this is the function. If it's greater than, is in between, then it's this function. So yeah, that's the brief idea of question 2. Okay, thank you so much.